Hello class, today we're going to be talking about derivatives and their connections to graphs of functions and tangent lines. Before we dive further into that though, it's important to discuss the relationship between a secant and tangent line. A secant line passes through a curve at two different points, while a tangent line passes through at just one point. Let's call this point A and this point B. If point B approaches A on this line, we eventually just get to the tangent line. And that could be from any point. If we had a secant line over here, as that point approached, we would come to the tangent line. So, knowing this, we can say that a tangent line at point A is the limit of the secant line as B approaches A. So, knowing this, let's talk a little bit more about the slope and derivatives and how they can tie into that. Derivatives are the rate of change of a function or slope with respect to an individual variable. And we can use a derivative to find the slope of a tangent line. So, in order to find the slope of the secant line, let's look at this point x and x plus h. We're going to call this x plus h because we go, the distance of h away from x. So this is x and that's x plus h. We know that slope is rise over run, so we know that rise is x plus h minus f of x over h. Once again, being rise over run. So since we know a tangent line at a point is the limit of the secant line as it approaches it, we can use a limit definition to find the derivative, which would be the slope of our tangent line. So in order to find that, we find the limit as h approaches 0 of f of x plus h minus f of x over h. And once again, that will get us our derivative, which we can use to find a tangent line. So let's look at that. Let's look at an example problem. Find the equation of a line tangent to the function f of x equals 2x squared minus 4x plus 2 at the point 2, 4. So we know the derivative would be the slope of our tangent line, so let's find that first. In this situation, we're going to pretend that we know our power rule just for the sake of the longevity of the video. We're going to make it go a little quicker. So, in order to find the derivative of this function, we'll use our power rule. So, we'll bring the 2 down, which will give us 4x, and we subtract 1 from our exponent, so it just leaves us with 4x to the first power, or, just 4x. And then we do the same here. We subtract 1 from our current power, and we get 4x minus 4 as our derivative. So in order to find our slope for a tangent line, we're going to plug in our given point, which is 2, 4, but we're just going to use the x coordinate. So we'll find the derivative at 2, which will be 4 times 2 minus 4. We end up getting 8 minus 4. And of course, our answer will be 4, which is the slope of our tangent line. So to find our tangent line, all we have to do is use our point slope formula, which is y minus y1 equals mx minus x1. So let's plug in our values. Our 2 is our x value and our 4 is our y. So we have y minus 4 equals 4, which is our slope, or m, times x minus x1, which is 2. So now all we have to do is distribute and get y by itself. So 4 times x is 4x. 4 times 2 is 8, but it's negative. And of course it's y minus 4 equals this. So now we just have to add 4 to both sides. And we end up getting the equation y equals 4x minus 4. So this would be the equation I won't write it all out, but it would be the equation of the line tangent to the function. So let's talk about other ways that derivatives can tell us things about graphs. Let's go ahead and just look at this function again, which was f of x equals 2x squared minus 4x plus 2. If we find our first derivative, this can tell us about extrema and when our graph is increasing and decreasing. So let's go ahead and get our derivative, which we had already found, was 4x minus 4. If we set this equal to 0, we can find our critical numbers. And our critical numbers, as I'll show you in a minute, once again, it'll tell us about if we have a max or min, and when the graph will be increasing and decreasing. So saying that equal to 0, we have 4x equals 4 divided by 4, x equals 1. That would be where our critical number is. Also known as Cn. So in order to find out if this is a max or min, we can set it up in a chart. Have 1 up there. We'll pick a number smaller than 1 and bigger than 1. So let's go 0 and 2. If we plug in 0 into our derivative function, we will get 0 minus 4. That's a negative number. And if we plug 2 into this function, we would get 8 minus 4, which is a positive number. So by seeing that, we can see that our graph is decreasing all the way to 1, and then at 1, it is going to increase up until infinity. And we also know that if it's decreasing and increasing, we have a minimum at x equals 1. And we could plug that into our original function to find the exact point, but once again, we won't do that for longevity purposes. We can find even more we can see even more on our graph if we find our second derivative. So I need a little bigger equation, a little longer equation, so we're going to use the equation 2x cubed minus 3x squared minus 3x plus 8. We're first going to find the first derivative, and then we'll find the second derivative, which will tell us about inflection points, possible inflection points we may have, which can tell us about the concavity of our graph. So let's first find the first derivative. We use our power rule. We'll have 6x squared minus 6x minus 36. Let's go ahead and find our critical numbers. We'll do that by factoring out our 6. And then factoring this to become 6 times x minus 3 and x plus 2. If we set that equal to 0, we know we'll have critical numbers at x equals 3 and at x equals negative 2. All right, now that we have our critical numbers, we could set up our graph and we could find increasing, decreasing points, max and mins. But for now, let's just skip to our second derivative. So if we use this, we can find our second derivative, which would be 12x minus 6. If we set this to 0, we will find possible inflection points. We won't know if it's inflection point until we set up our table here in a minute. So doing this, we are able to find that 12x divided by 12. We have a possible inflection point at x equals 1/2. So similar to our critical numbers, we'll set it up on a table. And fortunately, we can use these numbers on this table. We'll put negative 2 and 3 over here. And if this ends up being an inflection point, it will also just be a quicker way of telling us if these numbers are max or mins. So let's plug these two numbers into our second derivative. If we plug negative 2 in, we get negative 24 minus 6. That is a negative number. And if we plug 3 in, we get 36 minus 6, and that is a positive number. So we do have an inflection point. We have a negative concavity here and a positive concavity here. And this also helps us see that we have a minimum at 3 and a maximum at -2. So as you can see, derivatives can show us many different things on a graph, and we can use derivatives to find the slope of tangent lines. And why would these things be important in the real world? When would we use derivatives in real life? Well, we can use derivatives to calculate business profits and losses using graphs. And we can also check temperature variation as well on graphs. And we can determine speed or distances covered over amounts of time. So that's why derivatives are very important, and I'm glad that we got to learn more today about their connections to graphs of functions and tangent lines.